let's start. So I wanted to mention about last time, I had a small mistake in the numerical verification, that we have a right solution, if you remember. So I just wanted to say a couple of words on that. So the thing is that you have to integrate away from the infinity towards the point you want to, right? So what we had is a function that blows up at x equals 0. So when you do the numerics, what it does is takes a point. I also updated the file. So the updated file shows all of this. So when you integrate, let's say you start from x equals 1, and you want to see your solution tells you how the function behaves, right? How the function behaves when x goes to 0. So what you do, you should take some initial point. Doesn't matter which point you choose, right? Because it just sets the initial condition, the constant. And then what MATLAB or Wolfram, whatever you choose, does is it integrates towards the direction you want. So we want to integrate away from the singularity towards the singularity. Because if you start here and integrate, right? Let's say you start here and integrate, right? So you start here and integrate down. What happens is, because this function explodes at 0, the numerics go crazy and you can't really compute what's going on, okay? And as you approach the point 0 from 1, it also starts to go crazy, but you can increase the accuracy in MATLAB, and you have a precision parameter you can increase. Right. So if it's 10 to the minus 8 or whatever, so you can increase this, and then it will explode. You will have nonsense a bit closer to 0. So it would look like, I'll take another color. So you will have something that goes like this, and then when it's too steep, right, then you'll get nonsense, right, or something like this. So this will make the nonsense a bit shorter, but you can see the general idea that it works, right? And you also, so what I plotted, it was from x equals to 1 towards x 0.01, right? So if you increase accuracy, then you can integrate over 0.01, etc. And you'll have a smooth function.
אבל אם אתה נגיד עושה לצורך העניין את הדבר הזה, הפונקציה שלך שם מתבדלת, הייתי מצפה שתהיה לי תרומה מאוד משמעותית מהאינטגרל ליד הנקודה הבעייתית.
Yeah, so you should look at the notes, but no, it's correct. You capture the behavior. It just explodes very rapidly, and there's a limit to the precision. That's a problem. So the precision of the numerics is what limits you. But the answer is still correct. Yeah, but it's 1 over this. It's accuracy, right? When you integrate, so I don't want to get into this, but it just depends on numerics. So the numerics, the precision tells you how close you can get to a saddle point before exploding, but it doesn't really matter. I just wanted to show you a basic concept. So you should integrate when you're sufficiently far from the singularity toward the singularity. That's the idea. So I did it the other way, and that's why I got nonsense, and now you know. So let's get back to what we're here for today. Okay. So David talked to you about Laplace's method, yes. Watson's lemma, right? Yeah. Movable maxima you talked about. Mm-hmm. Okay. So I wanted to start method of stationary phase. Okay, and then we also have a more generalization of the stationary phase afterwards. But let's start from here. By the way, I had a few more examples for Laplace method that I didn't have time to talk about, so I will upload them to the Moodle as well, so you can check it out. Okay, so method of stationary phase. So we want to generalize the integral. It looks like this. Right? So Laplace's method applies. Laplace's method considers only when phi, right, is real.
X to infinity, right?
Yeah, and x goes to infinity. Yeah. So we're still at x goes to infinity, but this is like a special case. So you want to generalize this. So first, let's consider that f is not necessarily real. Okay. So this is very trivial. So you can just say that f of t is you can just split it apart. So you'll have real of f of t plus I imaginary f of t. Okay? And then you can do the Laplace method pretty simply, right? So you can just, we'll have here the real part e to the x phi of t, right? You can take the I outside, and the imaginary part is also real. And you can just do the same game. We'll change.
You want a marker?
I had a few more, but we'll see if I'll need. Yeah, this looks okay. Okay. And then you can just do Laplace for this, no problem. Okay. But what if phi itself is imaginary?
אז אתה בעצם רוצה להציע בשלב הראשון שתעשה לפלאס מethod לכל אחד בנפרד?
Yeah, so for this we just do separately the Laplace method for each one, right?
Okay.
So you just split it into two, so it's trivial. The question is, if this is imaginary, what do you do now?
אם זה מורכב טהור או שזה כאילו מדומה?
So we'll consider all cases. So first, the most simple case is that phi is purely imaginary. So this is the Fourier integral. Okay.
כל מספר מורכב אתה יכול להפריד לפאזה ממשית כפול קוסינוס פלוס I סינוס, אז אתה יכול לפתור מזה כאילו.
Yeah, but we want to use Laplace's method, right?
Yeah,
so the idea is, how do you transform your integral in a form that suits Laplace's method, right? So you need an exponent. So if you have if the power of the exponent is imaginary, then you can't just do cosine and sine, because then again you have a problem. You can't use Laplace's method. So let's consider that, which letter did I call this? This is psi. Right? X, I, psi. Yeah. So, right, this is psi? Yeah. Okay, so let's say that phi of t is I psi of t, and psi of t is real, okay? So this is called the Fourier integral. Okay. This is also, we consider the case of x goes to infinity, one approximate method. So to get an intuition what happens, you can always use integration by parts. Okay. So we will start with that, and we'll see what happens, and then we'll get some intuition on how the function behaves and what we can do. Okay. Also, there's a nice technique we'll see in a second that is also useful later for a stationary phase. Okay, so we use integration by parts. Let's consider the following example. So integration by parts doesn't always work, but we'll start with an example that it does, okay?
אתה מתכוון להשתמש באינטגרל פורייר באיזשהו שלב פשוט?
Sorry?
איך אתה מתכוון להשתמש באינטגרל פורייר פה בדיוק?
No, I'm just saying what this is called.
אוקיי.
A question that looks like this is called a Fourier integral.
אוקיי, ועכשיו אנחנו נפתור מקרה כזה.
Yeah, so this is an example. So as I said, integration by parts doesn't always work, but for this particular example it does, okay? So we consider this function g, this is f prime, right? So we have xp over ix square root of t on 0, okay? And now we need to integrate the other one, differentiate, sorry.
מי קראת גמא? קראת לשורש גמא?
What? This is g, this is f prime. I'm just using,
כן,
in my head, that's what I do, right? So fg, right? ab minus,
נגזר שהשני כבר ראשון.
yeah, f prime, g. Okay. Okay. So here, luckily, when you plug in the boundary limits, right, you get something finite. So we already know how this function behaves because the next term would be much smaller than this one, right? You see we're dividing by x, okay? So this is minus I over x, e to the ix, okay? And we'll call this I, this thing here. And it turns out computing this is not very simple because when t goes to 0, this explodes, right? So you can't keep doing integration by parts because in the boundary you get something that explodes, right? You get 1 over t or 1 over t to the power of 3.5, right? So you can do it. So we're gonna, yeah, so we're gonna use something else. We're just gonna solve it exactly. And we'll show that what the solution is. And the idea of how we solve it is used to prove how stationary phase later is, why it's correct, right? So the proof for stationary phase, the method, uses this as well. So that's why I thought this would be a good idea. Okay, so we have the following. Right? Okay. So the idea is that we wanna somehow transform this integral into a gamma form, right? So for gamma form, we need to have something at the exponent which is a constant, not a constant, sorry, not imaginary, right? We don't want something imaginary. So we do the following. So we'll start from this and then I'll cancel the imaginary part as well. But we want here to be a single variable. So we wanna, transform to gamma form, right? So I don't know what's the argument, I just wrote 2 dots, okay? So it's a gamma of something, we wanna find what it is. So we start with s equals xt, so ds to dt is x. Substitution, so we get now I over 2x, 0 to x, e to the is over s over square root of x. ds over x. Okay, and this is, so we're taking the limit of x goes to infinity, so we can switch this to infinity. Okay, we'll take all the x's outside, and we'll have I over 2x 3.5, 0 to infinity, e to the is, square root of s ds. This is at x goes to plus infinity. So this is an integral that shows up quite frequently, okay? And now we're going to show how this is connected to the gamma function. Well, the problem is we have an exponent here, okay? So the idea is the following. We're going to set another new variable, so s is iq, okay? So previously s was a real variable on the real line, okay? And now we're going to switch to the complex plane, and then we're going to do a bit of a trick to, I'll show you in a second. So to have it in a gamma form, we can't have an imaginary thing here, okay? Okay, for substitution, so I is 0 minus I infinity, e to the minus q over iq square root I dq. Okay? So the idea is the following. Let's see if I have another color. So if you're looking at the, no, it doesn't work. Yeah, so I'm doing it in a second. Yeah. So we have a complex plane. Okay. So what we had before, the idea is this is the real part, this is the imaginary part. Okay, this is some point radius r, ri, this is point r, this is point minus r. And okay, this is minus ri. Okay, so what we want to do, we want to show that this integral in the complex plane would be equivalent to the one in the real plane, okay? So we want to show that if we integrate in this area, it's the same as here. So we can use for this Cauchy's theorem, and right, so we want to show that if we integrate this way, right? So the integration over, yeah, so integration over a closed path is 0. You can also use Cauchy's or the residue theorem. The problem with residue theorem that you have here as saddle points, you'll have to do another like small radius here, and then take the radius of this to be epsilon. Epsilon goes to 0, but the idea is the same. And we're going to show that the integral over this curve is 0. Okay, so the integral on the imaginary line is the same as the integral on the real line. And then we can just switch here from 0 to infinity instead of 0 from minus I infinity. Okay, and then you can use the gamma function. Okay, so a nice trick also. So here we have I over square root of I. And we can use the fact that this is also very useful, that e to the I pi over 2 is I. Okay? Right? Because cos plus I sine. Okay. So square root of I would be e to the I pi over 4. And this would be, so I is e to the I pi over 4. Okay. Y.
המוחק שם ללוח נראה לי הרבה יותר.
She said this one is better. I don't know. I think what's one better? No.
No, it's not.
No. You need to apply more force.
Not worth it.
Okay. So we know that the complete integral over, by the way, so in the book he calls this like rotating the integral around the real axis with the imaginary by multiplying, by moving it I pi over 2, right? So that's what he calls it. But this essentially means this, okay?
I have a question.
Yeah.
Did we have to do integration by parts to do this method, or could we just done this method from the beginning of the equation?
What do you mean? The integration by parts at the start?
Yeah, from the start. If we ignore the integration by parts and try to do straight away to convert it to the gamma function.
Oh, on this one?
Yes.
Apply integration by parts on this?
No, I'm saying in the original integral, we did integration by parts in the beginning, right?
Yeah.
So if we didn't do integration by parts and we straight away would have tried to do what you're doing now, would it have been possible to solve?
Let's see, what does it look like? Nope.
Why not?
So would it work? I'm not sure. So it's 0 to 1 square root of t e to the I x t d t, right?
Yes.
So we're asking if we can do this game straight away.
Yes.
So the question is if we can switch it to a gamma form.
Mm-hmm.
I'm not sure because the thing is you need to have an x here at the upper part so you can take it to infinity.
Wow.
And then you can use the gamma form. And here you can't really do that because you still didn't get the x outside,
I
right?
understand.
So it would be like an incomplete gamma function and then you'll have more disgusting things.
Mm-hmm.
So I think this way is more convenient. Because when you do this game, the x goes into the boundary, right?
Mm-hmm.
And then you can take x to infinity, and 0 to infinity is the gamma function. And here you had 0 to 1.
כן, אז כאילו, אבל לצורך העניין יכולת לקבוע איזה משתנה אחר, נגיד לצורך העניין t שווה ל-x כפול משהו, להחליף. או משהו בסגנון שזה. שאף אחד לא מנהל לך לעשות צוות.
We can do the same thing. So you'll have here.
בלי לבצע אינטגרציה בחלקים. אפשר כאילו לסמן איזה מישהו כ-X כפול משהו, ואפשר לפתור את זה, לסדר את זה.
I don't think you'll get something. Let's see. So you have g into the I x t, right? Now we do s equals x t, and so you have t is s over square root of x, square root. You have e to the I x t. I think it will explode. That's a problem. We'll have something that not goes like 1 over x. We'll get something that, and then, right, and dt is ds over x. X. And now let's also switch from 0 to x. Right? So you have here square root of s over x to the 1/4. So we have 1 over x, 5 over 4, right? Okay, and then
It's the same trick.
yeah, so you can do this apparently. Okay, so maybe, but the book does it the way I'm
Okay.
talking about. But either way, the idea is, I think, once you do integration by parts, you can almost with no effort already get the first behavior, right?
Mm-hmm.
So, but I'm not sure if this works or not. Seems like it does. But thing is, we're supposed to get also 1 over, right? Exponential. Well, you can check if you want if this works as well. Let's continue. Okay. So we were here. So we call all of this region of integration B, let's say. Okay. So this is a closed integral, and then you have 0 to minus IR plus integral over the radius R equals R, right? Plus R to 0. And this should be 0. Just call Cauchy's theorem. Oh, okay. So we want to show that this actually goes to 0. Okay. And then we'll just have that this equals this, and then it's pretty easy, right? So we show that the following integral d goes to 0 as R goes to infinity. So is R equals to R. Okay. So what we need to do is actually just integrate over, right, the angle. So integrate this way, right? Okay, from 0 to 2 pi. So this is actually, how do you say חסום? חסום, פונקציה חסומה. So this is actually limited, or I don't know how to say it in English, but once you plug in the radius, whereas the maximum magnitude the integral can get, right? So this whole thing is smaller than the integral at r, right, the magnitude. And you'll have e to the minus z, z minus half, is limited by e to the minus z, z minus half, right? And this is minus r over square root of r, right? And you can see that when r goes to infinity, this goes to 0, but this is smaller or equal than this, so this also goes to 0. Okay, and then the integral on this function would also be 0. Okay, so that's the idea. So now we have 0 to IR minus IR equals minus R0 from here. Okay, so we can flip it. So 0 to R. And we take r to infinity. So now we showed that this is equivalent to the same from 0 to infinity. So you can just have used the hand-waving arguments and just say it's okay if we switch it, and that's it. But that's the more thorough way to show that it's true. Okay.
רגע, אתה חושב שאת השורה האחרונה בבקשה? רגע, אז בעצם מה שאמרת שהשיטה שאנחנו רצינו ישר לבצע בלי אינטגרציה בחלקי, פשוט היה צריך לבדוק אותה יותר, ויש כאילו זו שיטה יותר straight forward להראות דברים. נכון? זה מה שאתה אמרת עכשיו. אמרת שמשהו עם להראות ישר החלפה וכל זה.
Yeah, we switched from the imaginary axis to the real one, and we showed that integration over here is the same as from here to here. So you can just do it straightforward, but this is the proof of why it's correct to do that. So now we have that I is e to the I pi over 4, 0 to infinity, e to the minus q over square root of q, dq, and this is the gamma function. This is the gamma of half, right? Because it's 1 minus alpha. And this is square root of pi. Okay? And you can also check that now we get in total for the integral a, that it's I over x, e to the ix plus I 2x 3.5. Okay.
יש שאלה.
Yeah.
למה אמרנו שהאינטגרל מ-r ל-0 יש לפניו מינוס? למה אתה רוצה לשים שם מינוס לפניו? כאילו, זה פשוט אינטגרל מ-r ל-0, למה לשים מינוס?
I just deleted it because it's on the. Yeah, it depends on. We do it this way. So if you do it this way, then so this will be plus, and this is so plus, right? And then we switch the sides. So it was on this side. We switched to the side, so I have a minus.
זאת אומרת, רגע, אתה בעצם אומר שהחלפת את כיוון האינטגרציה שלך?
Yeah, so like a minus, is just switching the...
לא, אבל כאילו כשאתה מגדיר את כיוון העקומה שלך והכל, יש לך כאילו משתנה כאילו את האלמנט האינטגרציה שכל...
Right, so we define it this way. So from here to here it would be 0 to minus IR, right?
כן.
And this way it's just R equals R, right?
כן.
And then you have from I, right? From I to 0, IR.
לא מ-R אתה מתכוון ל-X, לא מ-IR.
Yeah.
כן, ואז כזה, אוקיי.
And this is 0.
כן, מעולה. בסדר, נסיים עכשיו. ולמה אמרת שערך מוחלט של E בחזקת מינוס Z זה E בחזקת מינוס ערך מוחלט של Z?
This?
כי רק למה E בחזקת מינוס ערך מוחלט של Z זה שווה ל-E בחזקת מינוס Z אחרי הערכים מוחלטים.
This transition from here to here?
כן, רק את זה.
So this is from infi, you know the infi? So you take the absolute value would be, the absolute value of Z is constant, right? Because you're on the circle. So this would be smaller than the absolute value, that's it. So this is just complex analysis.
Okay.
The thing is, when we did what you asked before the integration by parts, you get that 1 over x to the 5 over 4, which is not the leading behavior we got here. And so I guess there's something incorrect in that calculation, because you shouldn't get a different leading behavior in x. So there's something fishy there. So I guess I'm missing something probably, but I don't think you can do it that way, because you should get the same answer. But I'll think about it. Maybe I'll have an answer next time. Okay. So we did this. Okay, so an important thing that we're not going to prove, but the book uses it quite a lot, is the Riemann Lebesgue. I don't know if I'm pronouncing it correctly. Lebesgue lemma. Okay, so I'll just call it RL for short, because it's too long to say. Okay, and write. So you did this in David, or you don't remember?
You know this?
Okay, so the idea is, if you have an integral of a form, and he uses this, how it's called, how do you say, sentence? What is it? Theorem. Yeah, he uses this theorem quite a lot in the book to prove pretty much half of a chapter. So if this exists, okay, it means that a to b f of t e to the I x t dt goes to 0, okay, at x, right, at x goes to infinity. And usually the way it goes to 0 is like 1 over x, usually. So we'll see when this doesn't happen. But the idea is we could have neglected the second term here by just saying, using this sentence to show that it's going to 0 and then neglecting it, right? So I'll show you an example as well. So the idea behind this is that this is oscillating. When x goes to infinity, this is oscillating very strongly, okay? So you have a function that from some point forward oscillates very strongly, right? And then the time spent under the curve and over the curve almost cancel each other out, right? That's the idea. And eventually, so the proof is very long, but this is the idea. Because it oscillates, so subintervals that are next to each other cancel each other out, and then when x goes to infinity. Yeah, okay. So we have also the extended Riemann lemma theorem, right? So it concerns with a more general integral. So if you have the following, and phi t is real, so this is also called a generalized Fourier transform, integral, sorry. So here, what is it called? Psi can be whatever. So it's more general, and so Ix goes to 0 as x goes to infinity if the following holds. So ft dt a to b exists, right? So exists means it just doesn't explode, okay? And psi of t is continuously differentiable. What is this? Continuously differentiable for a smaller one. Okay. And phi t is not constant. For any subinterval in a smaller than t, smaller than b. Okay. It is continuously differentiable. Okay, so we're gonna now see what this means, okay? What does this imply and why is this important? We're going to do something else. We're going to do the general Fourier integral. So we're going to do something that's more general, okay? More general means it's a stronger technique. So by the way, the idea that phi t is not constant is pretty important. So if you have something here that's a constant and x goes to infinity, okay, so you'll have oscillations that don't die out or can't be cancelled. So that's the idea. And so now let's consider the general Fourier transform. This one, okay. Okay, so let's start with integration by parts like we do always. X side of t. Okay. And then we have minus 1 over ix a to b f prime of t sine. Okay, so you can immediately see why psi can't really be constant in the subinterval, right? Because otherwise we get something exploding here, and then you need to do something else, which we will show. It's called the, what was the name? I forgot. Stationary phase, okay? So that's called the stationary point where the prime of psi is 0, because when it explodes, and then you're not sure if because around the point of most contribution, you have something that explodes and also oscillates, and then you're not sure if it can cancel out or not, but we'll see how we deal with that. So as long as this exists, f prime over psi prime, you can use now Riemann-Lebesgue lemma, and this goes to 0, right? This also, so the behavior is asymptotic to the first term, okay? You can neglect the second term entirely. Okay.
We know it exists.
So this is by what's it called? Extended RL, right? Yeah? What's the question?
אנחנו יודעים שזה לא מתפוצץ.
This one?
Yes.
Yes, because we're assuming that psi prime and f prime, this whole function is a smooth function which exists and not 0. Okay?
אנחנו לא אמרנו את זה, אבל...
I'm saying it now.
לא אמרנו את זה, אבל F תג ועל F.
I'm saying it now, yeah.
אבל F אמרנו את זה.
Where what?
על Xi אמרנו, אבל על F לא אמרנו, זאת נקודה בעצם.
So f exists only if this won't explode. If this explodes, then this won't exist. It's the same, a different way of saying it. And also,
Xi זה אותו דבר.
it's not constant, so the derivative won't be 0 at some point.
Yeah.
Okay?
Yeah.
So it's the same idea. So now we can say that I of x is the first term. Okay? First term when x goes to infinity. Forgot to say. Obviously, okay, everything is about x goes to infinity. Okay, so how do we use this now? So you can always do this as long as this prime exists, f exists, okay? Because if f is 0, also at this point, you also have a problem. So it's not all very trivial. Also, there's a special case how to deal with it. But for now, let's say that we have a stationary phase, which means that psi prime is 0 at some point, of t. So t equals to that point is the stationary phase, and now we're going to show how we solve that. Okay. So what if psi prime of t equals to 0 at the interval, right? If it's outside the interval, we don't have a problem. So this is a stationary point. Okay. And what we do is the following. So you can consider there are many points like that. Okay. And when you cut them into, you cut the integration region instead of A to B around these points. And then you need to treat every point separately. So you can assume there's only one point for now, right? And then you can generalize it for any number of points you want. So for simplicity, let's say that the stationary point is t equals a, okay? And the contribution would be mostly around this point. So we can say a plus epsilon, right? Plus a plus epsilon to b, okay? So this goes to 0 by RL, right?
Yes.
And this one is the most contributing factor because this explodes, right? And since it explodes, we can also say that epsilon goes to infinity because the most contributing, it's like Laplace's method.
אתה מניח שיהיה נקודה
Yeah.
בעייתית?
So we're assuming that t equals a is where psi prime of a equals 0. Okay, so I can always split I into region of integration where I can start from a. Okay.
כן, ואז אתה רוצה לטפל בחלק הבעייתי.
Yeah. So we're gonna deal only with that part now.
אבל מה קורה אם זה באמצע של התחום, לא בהכרח בקצוות, אז אתה רוצה...
Then split it and
זה
cut.
תחומים במקום שתיים?
Then you can cut it and then show that also by this RL it goes to 0 and do the same thing. And if you have 2 points, 3 points, then you'll have the sum of 2 integrals or 3
אם אתה
integrals.
רוצה לתת את זה שלושה תחומים, אחד זה מינוס אפסילון פלוס אפסילון סביב הנקודה הבעייתית ועוד שניים אחרים שיקחו לאפס.
Yeah. If it was at the middle, then you can say, right? So let's see, it's C, but the integration is from, so you left from A to C minus epsilon, C plus epsilon, right? And this is 0, right? This goes to 0. The next one also goes to 0, and then all this is contributing. So it's the same thing. Okay?
כי יש לך את הסינוס אפסילון, C פלוס אפסילון. ואתה כאילו מניח שעכשיו פה המעריך הוא ממשי, נכון? כאילו, מה אתה... פה כדי של VRL. VRL אנחנו לא משתמשים בשביל הפורייר אינטגרל.
So this is for the general, right? And B, if I remember, psi is only real, if I remember correctly, right? Yeah, psi is only real. And later we can do...
רגע, אז אתה עובד כ-extended RL, לא? למה?
Yeah, it doesn't matter. RL, extended, whatever. It just goes to 0. You check whichever you can use, but the idea it goes to 0 according to RL. I'll call both of them RL just for simplicity.
אוקיי, אבל כאילו אנחנו עדיין עובדים מאינטגרל פורייר, זה לצורך.
Yeah, so this is the generalized for you.
כן, כן,
Okay, so the idea that this goes like 1 over x. Okay, so now we do very similarly to what Laplace's method does. Okay, so we say we have a to a plus epsilon, and now we take f at a. Okay, then you have exp. When this is not real, it's another technique, which I don't know if we'll have time to talk about today, but let's see if we get there. So x, so we also extend the exponent around the max point, right? So you get psi of a plus 1 over p factorial psi of p derivative at point a t minus a to p, okay, dt, and p is the first derivative that is not zero. But so it's like generalized Laplace method, if you remember, right? P of a first to not be zero, and since the first derivative is zero, then p is bigger or equal to 2. First to not be 0, so p is bigger than 2, okay, or equal. So now we can switch again a to infinity, okay, and the idea that the infinity introduces terms that fall like 1 over x, okay, and we will see that this maximum point is more contributing than 1 over x, right? So it explodes
למה אתה מרחיב את זה כאינטגרל עד אינסוף?
less fast than 1 over x.
למה אתה מרחיב את האינטגרל עד אינסוף?
So you'll see in a second. It's like in Laplace's method. Where was I? Infinity, and now we set also s equals to t minus a. Okay. And then you'll get I of x is, can take all the constant outside. I x psi of a 0 to infinity exponent of ix over p factorial s to the power of p ds. Okay? So now if you remember, we want to transform again. We always want to transform into gamma form. So we need to get rid of the I, right? And also we have a power of S. So we don't want to have a power of S. So we substitute instead of S, U, and S would be u to the I pi over 2p. P prime u x psi of p a. Okay, so the idea is when you plug this in, because S is to the power of p, this turns into I, right? I times I is a minus, and then you can use Laplace's method. So you'll have u, you just have u, right? So you'll have minus u, exponent of minus u, and you can just use Laplace's method, and you'll get. So this is the case when psi of p at the point, right? The first derivative it isn't 0 is bigger than 0, right? But if it's a negative number, then you need to switch. Here will be a minus sign, okay?
Can you explain again the s equals all of that?
All this?
Yes.
Okay, so you have so this is basically I pi over 2, I divide by 2p, okay?
Okay.
And you remember that I is e to the I pi over 2.
Yes.
So as soon as this is s to the p, if you'll have this turns into an I, and I times I is a minus. Okay, so this whole thing will look like x of minus u, right? And you will see that you'll have here u1, you'll have here u1 minus 1 over p. That's what you'll get.
Oh.
Okay, and this is exactly gamma. Okay, so you need to have a minus here to be a gamma definition, right? So, and this is only if the derivative is positive. If it's in negative, then you need to have a minus here. So you'll have the minus u here again. Okay? So you'll have a minus if psi of p of a is smaller than 0. So he calls this is again the same idea as we did. Once you switch it, you get here 0 to I infinity, right? And again, you'll have the same thing like we did before in the complex plane. So you'll have like this integration from, let's say, to r, and when you take r to infinity later, you need to switch it by an angle, right? So you'll have the integration here, here. And he calls it by rotating your integration region by I pi over 2p. So this phi here is I pi over 2p. Pi over 2p, right? That's the idea. So this is the same game like we did last time. And now what you'll have, the integration over this part is the same as this one, right? And this goes to 0. So this goes to 0. Let's call it C2. So this goes to 0, right? In the same method we showed before that. And then so you'll have 0 to I infinity. It's the same as 0 to infinity after we switch to u. Okay? So you can check it if you want, but it's the same thing. But now we rotate by a small angle instead of pi over 2. So I'll show you the result. So we get I of x is f of a e to the ix psi of a plus minus I pi over 2p prime. So this is an absolute value because it depends on if it's positive or not. We'll have a plus minus here, right? That just means if we rotate this way or the other way, okay? 1 over p gamma of 1 over p. Okay, this is for x goes to infinity. Okay. Okay. So I can do an example now. What time is it? Okay, let's do an example.
רגע, לפני שאתה קובע את החוק, אני אסביר את החלק הזה של המעבר לפונקציות גמא.
Okay, so as I said, we want to switch to a form where the exponent is just minus u.
Okay.
And this is a substitution you have to do to accomplish this. Okay, so you can just do the substitution and you'll see. Okay.
זאת אומרת, פשוט רוצה להציג את הדבר הזה כדי שזה יעבוד, כדי שכל הדבר הזה יסתדר בצורה של רציתי שם.
Yeah. So I used this to transform into gamma function form. Okay, so this is what we get, and this is the gamma function.
אוקיי, ואיך אתה משתמש בזה לצורך העניין? אחרי אתה פשוט עושה את התהליך שעשינו לפני.
The problem is once you do the switch, then you have 0 to I infinity instead of 0 to infinity. And then we showed like before that 0 to I infinity is the same as 0 to infinity, right? Because of this.
Okay.
So you can use the gamma function. So you'll have your 0 to infinity, and that's it. Okay? And this is what you get after you.
כן, אבל כשאתה רוצה לגזור את הביטוי הזה אחר כך, אתה לא רוצה לקבל, כאילו לך את השם קומלנט, שאתה צריך להיפך קבוצה. כל מיני גורמים של ds, כאילו שיהיו צמודים שם, כשאתה אומר את זה ds ל-du משהו. שאתה רוצה להחליט את השם.
Yeah, I took it in, I just didn't write it. It's here, I just didn't write it. Okay, it's v over p and all this stuff. I didn't neglect them.
Okay, so
Okay, example. So this is example 5 from the book. So this is a Bessel function for integer values of n. So you can show that it's the solution of the following integral. Okay, so n is an integer, and we take the particular problem of x equals to n, and x goes to infinity. Okay, so we want to solve this problem. So how would you suggest transforming into the stationary phase form to solve this? Have an idea? You need like the... Sorry?
בוא אפשר לנסות לפרק את קוסמוס. קוסמוס זה 1 פלוס, ואז אולי בפנים אין את ה-x.
No, there's an easier way. Instead of... So you have an idea?
לפרק את זה לקוסמוס של מינוס שתי זוויות ותקבל כמה גורמים שם.
No, even more simple. So you can just use, you wanna, with a general Fourier integral, right? So you want e to the I something. So e to the I something, if you take the real part of it, you get cosine. So that's what you can do here. So you can calculate the integral and then take only the real part, and that will be the original one. So you will have 1 over pi real of 0 to pi x I n sine t minus t dt. Okay? So this would be our psi grid function, okay. And now the question is, do we have a stationary phase, right? If we have a stationary phase, then we need to use yeah, what we just did instead of regular techniques, right? So otherwise we could have just used integration by parts. So here you can see the psi prime of t is cosine of t minus 1. We should be 0, right? And so t equals 0 is the stationary point, and it is inside the integration region, and it's also on the boundary, so life is easy. So you can just do it now from 0 to infinity and take this point. Okay, so the idea is, when is the first derivative of psi that is not 0? Then we know what p is, and then we can just plug into our formula for p, right? So let's take the second derivative. So the second derivative is sine, which is also 0 at t 0, right? So we have to take the third one. So the third one is minus 1. Right, at t equals 0. Minus 1 at t equals 0. Okay. No, sorry, 1, right? Minus?
No,
1.
1,
Yeah, 1. So we can take the p formula for p equals 3, right? And we need to take the positive formula with the plus over the I, and we get, so p is 3, and after plugging in the formula, it is quite simple, so we'll just get 1 over pi real of 1 over 3 minus I pi over 6, 6 over n, thirds, gamma of 1/8. No, 1/3, sorry. Which is 1 over pi, 2 minus 2/3, 3 minus 1/6, gamma of 1 minus 3, and minus. Okay. Okay.
What difference would it make if it wasn't on the boundary? Let's say if it was in the middle of the boundary.
If it was on the middle, then it will make a difference.
It wouldn't?
No.
Oh, okay.
Because you expand the function around this point. So only the contribution from this point is what dominates. So it doesn't matter. We just did it for simplicity in how cutting the subplanes. Okay, so now method of steepest descent. steepest descent. Okay, so now we're taking an even more general integral, which looks like this. Right, and now rho can be both real and imaginary. Okay, and t is also a complex number, and we're integrating around the contour C, which is in the complex plane. Okay. Okay, so the general idea of steepest descent, you want to shift the contour where rho of t is a constant imaginary part. Okay. Okay, so rho t has a constant imaginary part, so we shift the contour in such a way that rho t is a constant imaginary part, and then we can use Laplace method, because as soon as it's constant, you can take the imaginary part outside of the integral, so you'll have Ix, let's say it's psi, right? So psi is constant, ht e to the x phi of t, okay? And then we apply Laplace's method on this. Okay, so the idea is we switch from C to C prime, and, or C, I don't know, call it C1, whatever. And we switch it in such a way that rho t is a constant imaginary part, you can take it out. So, what's interesting about this is how you shift the contour, right? And it turns out that the contour where the imaginary part is constant is also the direction of steepest descent. Okay.
אמרת שהסטיבון just descent, מה?
I will write it as well, yeah. So the direction where the contour, right? It's contour where image of rho is constant is also the path of steepest descent. What do you mean by steepest descent? It means that the exponent here goes down, right? If it goes down, then you can use Laplace method. Because if it goes down, then it has a maximum, right? So maximum doesn't have to be a real maximum, but a maximum in the region. So as long as the function goes down, then you can take the value at the starting point, and that's the maximum of the region, right? So this ensures that you can use Laplace method. Okay. The steepest descent. So I will also show examples and be more understandable. So I do that. Should I delete something? Okay. So example. Okay, so let's look at the following integral. X goes infinity. Okay. So if you want to do the previous method we showed with the stationary points, right? So we can see that there is no stationary point, right? So the function phi of t is t. So the derivative is just 1. So there's no stationary point, so you can't use the method of, what was it called? Phase something. I always forget.
Stationary phase.
Sorry?
Stationary phase.
Yeah, stationary phase. Okay. No stationary point. No stationary phase. And also integration by parts fails. Right? Why does it fail? So you can see it immediately. Yeah, so the ln at 0 doesn't exist, right? Doesn't exist, so you can't use integration by parts. And the idea is that integration by parts always gives you, so the powers of x always goes to, right? So if the expansion is in powers of x to the power of minus p, then you can use integration by parts. But if your behavior is not like this, then integration by parts won't give you the correct answer. And you will see in a second the correct answer is 1 over ln of x. So integration by parts can never give you something like that. But it's a problem. Integration by parts always gives you some power of x. That's what I'm saying. So, and p is bigger than 0. So the behavior always goes like 1 over x to the power of something in integration by parts, right? Because every time you integrate, you get 1 over x, 1 over x squared, etc. That's the problem. So you'll never have ln or something like that. Okay.
לכן אבל אם היית עושה אינטגרציה בחלקים היית מקבל 1 חלקי x, כאילו, אם היית לוקח לן כזה שלך. זה לא היה פותר לך את הבעיה פשוט.
Also no. Okay, so the idea is you want to find where the imaginary part of rho of t is constant, right? So you know that rho of t is it, right? It. And we treat t as being in the complex plane. Let's say that t is u plus iv. We're going to do it the other way around. No, yeah, so t is u plus iv. So rho is now u I minus v. Okay? So you need to look at the complex plane. Yeah, I'm just doing this. So you have the complex plane. Okay, we have here 0, this is u, v. Okay. The original integrals from 0 to 1 on u. Right, so this is the original one. So we want to look at what's the imaginary part at 0, right? We want some trajectory that's starting from 0, which has a constant imaginary part, but any path that goes through 0 will have the imaginary part of this point, right? So the imaginary part of this point is 0, right? V is 0. So we can conclude that we only have 2 paths now, right? Any other path would give you an imaginary part of V, right? You want a constant one. So you have 2 possibilities, go up or down. So usually when you have 2 possibilities, right, then one of them is the steepest descent, and then one of them is the what's the other one called? You have steepest descent and steepest ascent, right? Ascent. So one of them grows and one of them goes to 0.
But if you go on the V plane and it's not constant, the imaginary part.
No, wait. What am I doing wrong? No, we want the imaginary part of rho to be 0.
You want the imaginary part.
And you multiply I by t. So multiply t by I.
I see.
Right?
Okay.
So it's the other way around.
Mm-hmm.
Right? So imaginary part of rho of t is u.
Yes.
And u is 0 at t equals 0. So it has to remain 0. Okay? So u has to remain 0 and you go up here. So that now we need to check if going up is the descent or the ascent. Right? So how we do this? So we want to use the Laplace method, right? So what we want to do is we want the exponent to go down. Then you'll have a maximum. So you have x rho of t, right? And we know that the imaginary part is 0, so this is very simple. It's just x of minus x v, right? Because you just have minus v, here is 0. So you have minus xv. So you know that if v goes up, this goes down. And if v goes down, then this goes up.
Right.
So the descent would be upwards. Okay, so we choose the upwards direction. And we also do it to it, right? And we take afterwards t to infinity. You'll understand in a second. And the same thing goes here. This path also gives you the same direction. You can do it as well if you want, with the same idea here.
רגע, אבל אם v עולה, אז אתה בעצם אמור לפתון פה בסך הכל, לא? כאילו v עולה, אז e לעשות מינוס x, v אמור לפתון.
But x goes to infinity.
Okay,
So x is positive, v goes to be even more positive.
אוקיי, אז אתה שם מינוס.
So e to the something negative goes to 0.
כן, אבל אתה לא רוצה שזה יעלה?
No, no, you want descent. For the Laplace method, you want a descent,
אוקיי, כן.
right?
כן, כן.
Because if it always goes up, then you'll never have a maxima. Okay, so the same thing goes here, and then you need to connect it in this way, right? So you find this, you need to connect them, and this is 1 plus it. And you can show that the integral, this path is 0. Okay. So why is it 0? You can use again the RL that we showed before. We can do it explicitly if you want. So our was ln t e to the ixt, and now we have it2, right? So let's call this C1, C2, C3, okay? So we say that the integral on C2 ln t e to the ixt goes to 0, right? When t goes to 0. infinity, sorry, right? And this is true because you can show, so you have it plus 1 ln t ext. So according to our L, what we want to show is that if this is finite, then it goes to 0. And obviously it is, okay? Because of a 1, okay? So you can show this is finite, and then according to our L, this is 0, okay? So now you just need to integrate over this, and this region you'll get this one from Cauchy's theorem, okay? So let's do that. Oh, okay. So we have I of x is now 0 to it ln of t e to the ixt minus, because it goes down now, right? Down means it's a minus 1 plus it ln of t e to the ixt dt, okay? So now we switch variables, so this would be t is is, and here t would be 1 plus is. Okay, so this is again, we want to switch to a gamma form-ish integral, okay? And we'll use a couple of tricks to evaluate this in a second, we'll see. I'll finish in 5 minutes. Okay, so I 0 to infinity ln of is e to the minus xs minus I to infinity okay, so this is, we call this I1, this we call I2, okay? So I1, so ln of is you can actually separate the I and s, right? So it's ln s plus ln I, and ln I we know what it is, it's pi over 2, because e to the power of I pi over 2 is I, right? So we can do that, so we have ln s plus ln I e to the minus xs ds, this is I pi over 2. Again, we switch variables because we want to have a familiar integral. So usually in the exponent you want to have just minus u. So we set u is equals xs, right? Du to ds is x. And you'll have I 0 to infinity u divided by x plus I pi over 2 d minus u u over x. This is I over x 0 to infinity ln u e minus u. And this is an integral that you should know, right? So this is Euler's number, gamma, okay? If you remember, like 1 over n, right? So you can show it's the same. So we have this minus I ln x to infinity e minus u du pi over 2x. So this is easy to compute, right? This is also easy, and you'll just get the answer. And for the second integral, you need to use Watson's lemma. You remember Watson's lemma? So the idea is you expand a function that comes before the exponent into a series. And as soon as you do that, you have powers of t. Yeah, so I'm doing, no, I'm just talking in general.
Second part.
Yeah, I'm doing it on this, on I2,
Oh,
sorry.
okay, good.
So I'm doing this, an expansion,
Yeah.
and then you'll have powers of s, and powers of s times exponent of s is gamma function. So we'll have a series of gamma functions, okay? So that's the idea. So you want me to do it, or? Okay,
I have to go. Thank you very much.
no problem, bye-bye.
רגע, אבל יש עוד ספר בסוף
יש לי פגישה עם תודה.
So we show this 0 to infinity, ln of 1 plus IS. And what am I missing? E to the ix 1 plus is, right? ds. So expand now the ln function. So ln of 1 plus is is minus is to the power of n over n. Okay. Now you can apply Watson's lemma. So Watson's lemma is So Watson's lemma is, if we have a function ft e to the minus xt dt a to b, okay, so we expand ft, and the max is at t equals 0, right? So we expand ft around t equals 0, so we plug in ft is a series, a n t beta times n, and then I would be a n 0 to infinity e to the minus xt t to the power of alpha plus beta n, right? So I just took the constants outside, and this is the form of a gamma function. So you can set s equals xt to get the gamma form function.
כן.
2 minutes.
סליחה.
Gamma of alpha plus beta n plus 1.
יו, זכרתי שיש לך
Okay, so we do the same here, and we get for I2 x is I e I x minus 1 n minus 1 x n plus 1, right? When x goes to infinity. Okay.
איך זה הפכת מגמא למינוס 1 כפול n נוסחת צלת אותה?
So it's the ANs. ANs give you the minus 1, minus, right?
כן. איך הגמא אבל
And-
הפכת את הדבר הזה?
Sorry?
הפכת את הגמא למשהו אחר, לא? רגע, איך הפכת את הגמא למה שזה היה פה? מצד ימין, שאמרת לי ב-I2.
So you just need to know what alpha and beta is, right? So what we have here, we have IS. So what would alpha be here? You need to also switch variables, right? You need to switch variables as well, instead of the IS, right? Because you need to have minus x times t. No, you can take e to the ix outside, then you have e to the minus xs. So it's okay. So I don't need to do anything. So you have e to the ix times e to the minus xs, right? So this is exactly this. So you have s instead of t, and you can plug this in. So yeah. So this is a sum. So the divide by n turns into probably this. But you can do it. It's not.
זאת אומרת, זה אומר שיש דרך של להגיע משם לשם, זה מה שאתה בעצם.
Yeah, I'm just. This is a formula. This is what you get. Yeah. So okay.
והסכום של I, מ-n שווה 0 עד אינסוף.
איפה?
הסכום של I כאן למטה, בשורה התחתונה. הסכום של I שואף ל...
זה?
לא, H2, מדבר על I, למטה. בשורה הכי תחתונה פה.
פה?
כן, מאיפה לפה?
זה 0 עד אינסוף.
מאיפה לסוף, אוקיי, סבבה. עכשיו, לגבי מה שרציתי לשאול. כשאתה אמרת שצריך לעשות את הגרפים רק לשתי שאלות, אתה התכוונת לשני סעיפים שם?
מה שתבחר.
שני סעיפים, והסעיף בונוס הוא חובה גם, כן?
לא.
אוקיי, עכשיו שנייה. לגבי השיטה פה של המתוד